Okay, so the first lab, actually the first two labs, we're just going to learn some basic statistics and basic Excel. And the reason we do that is because we're going to be using it the entire semester. And what I found is that many students don't know these basics. So let's just do it. All right, so statistics, part 1. Let's pretend we have a clock in this room. Just one of those, big wall clocks. And I'm going to do the following. We're going to use the clock, which you can't see, but that's okay. We're going to use the wall clock to time how long it takes this marker to hit the ground. All right, so ready, 1, 2, 3, go! Okay, so we're going to use that wall clock, just an ordinary wall clock, nothing special. And according to me, using that crummy old wall clock, the time it took to reach the floor was 1.2, 3, 4, 5, 6, 7, 8, 9, 10. There. All right? So that's how much time it took from the time it left my hand to reach the floor. What do you think? Do you believe it? You better not. How could I possibly get this kind of precision using, one of these wall clocks, where the arm goes beep, 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 beep. Totally impossible, right? Totally impossible. So, totally ridiculous. So, what do we do? I mean, let's look at this. Let's say here's a meter stick, right? Let's say I use a meter stick to measure the thickness of the width of this piece of paper. I mean, I couldn't say, 0.529, 7345, blah, 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 I mean, so what's the rule? What's reasonable? What do you do when you're trying to make measurements and you just have, you have something to have a clock or a meter stick or whatnot? All right, so this is significant figures. Okay, measurements are known only to within the limits of experimental uncertainty. Okay, that kind of makes sense, right? Because there's no such thing as a perfect measuring device, All right, and so here's the general rule. We're not going to follow it sometimes because sometimes it's ridiculous, but we're going to follow it most of the time. So there's a general rule. What you do, you estimate 10 divisions between the smallest marked scale division, and that's all you can do. So for example, here. So what you do, I'm assuming these are centimeters, right? So let's say these are centimeters. Yeah, it's a centimeter because it's 100. Yeah, okay. So these are centimeters. So when you're measuring something, you kind of divide this by 10, right, millimeters, and then the best you can do is say something is so many millimeters long. Okay, so all right, so like if on a clock, if it just has seconds, that's the smallest marked division, seconds, then you can estimate something to 1/10 of a second, but no more. Okay, and we'll have a lab later on where you can't even do that, or like we'll have a lab where you can't even estimate to 1/10 of a centimeter. So you just do centimeters. All right? So again, estimate 10 divisions between the smallest marked scale division. Okay, great. Now, how do you express that mathematically? You express that mathematically by significant figures. Okay? Significant figures. By the way, I do care about significant figures in lab because we're making measurements. I don't care about significant figures in class because we're not making measurements, all right? I mean, so don't worry about significant figures in class and on your problem sets. Only worry about significant figures in lab. Now, some people completely disagree with that. Some people make their students worry about significant figures in class. Oh, I don't. Okay, so by the way, significant figures, too many syllables, so I just say sig figs. That's what most people do, right? Sig figs. Okay, so all right, here's how you got to figure out the number of sig figs. Okay. So here we go. The most significant digit is the leftmost non-zero digit, okay? So that's the most. Leftmost non-zero digit. All right, so what is it? what's the leftmost non-zero digit? Well, 1, right? 1, okay? That's the most significant digit. All right, now what is it here? Okay, the most significant digit is the leftmost non-zero digit. What is it? It's this one, right? This 5. Okay, so that's the most. Now we're going to learn about the least. Okay, now it's a little bit more complicated. If there is no decimal point, the rightmost non-zero digit is the least significant digit. Okay, so no decimal point, rightmost non-zero. If there is a decimal point, the rightmost digit is the least significant digit, regardless of whether it's 0 or not. Okay, so here's a number. There's no decimal point. So what is the rightmost non-zero digit? Well, it's a 6. Agree? So this is the least significant digit. Okay? No decimal point, rightmost non-zero. Okay, now we have a decimal point. So what's the least significant digit? Just the rightmost digit, right? So it's just 0. Okay? All right. Okay. What is it here? What's the least significant digit? The 6. Agree? The rightmost non-zero. Okay, so we have the most, we have the least. So what we want to do is we want to figure out how many sig figs there are. So the number of sig figs is found by counting the places from the most to the least. Kind of makes sense, right? Okay, so what's the most? Oops, sorry. We're supposed to see that. What's the most? 7. What's the least? 0, because there's a decimal point, right? So how many sig figs are there? 5. Okay, all right, so what's the most? I wish we were in class, right? What's the most? 6. What's the least? 0. How many sig figs? 1, 2, 3, 4, 5, 6. All right, okay, so you have to understand that, obviously. Now, what we're going to be doing is we're going to be doing mathematical computations, right? Mostly multiplying and dividing. So I don't care about adding and subtracting because we almost never do it. Okay, multiplying and dividing. So here's kind of like the motto here. A chain is only as strong as its weakest link, right? If you have this incredibly strong chain, but you have a really weak link, well, the chain's junk, right? Because it has a weak link. It's the same thing with mathematical computations. If you're multiplying a bunch of numbers, but one of them, you don't have very many sig figs, well, then the answer can't have very many sig figs, right? Okay, so we got to figure this how to do it. All right, so multiplying, dividing, which is what we're going to be doing. So the final answer, so the number of sig figs in the final answer equals the smallest number of sig figs in the original factors. Okay? So here's an example. So we have 5.4 meters multiplied by 67.56 meters. You put it in your calculator and you get this. However, remember, the number of sig figs in the answer is equal to the smallest number of sig figs in the factors. Okay, so how many sig figs do we have here? 4. How many here? 2. So how many sig figs can we have in our answer? 2. So you get to round this thing, 2 sig figs. So you round it and you get 360 meters squared, right? There's no decimal point, 2 sig figs. Okay, now I'm going to try to trick you. Let's see how many people I can trick. Okay. What should be the answer? Why? Because this is not a measurement, right? There's no units here. It's not a measurement. Okay? This is the measurement. 4 sig figs in the measurement, so 4 sig figs in the answer. Remember, sig figs only go along with measurements. Okay? So I did that on purpose. Okay, I'm rotten, I admit it. Okay, so that's sig figs. We'll be doing that a lot, especially today's lab. A lot of sig figs. Okay, let's talk about errors. All right, so we're going to talk about 3 main types of errors. The first type we call personal errors, basically mistakes. You did something wrong. You didn't follow the directions or whatever. So you can look at that. We don't want to make personal errors, okay? Second one, systematic errors. They're usually caused by equipment. Now look, there's no such thing as a perfect piece of equipment, all right? So systematic errors tend to be, in the same direction. Like if you have a voltmeter, and let's say like all the readings are a little bit high, or all the readings are a little bit low, or something like that. You try to reduce these systematic errors as much as you can, right? So like with a voltmeter, you calibrate it. So you calibrate it so 0 is 0. But come on, you're never going to get it exactly. So if you have an experiment with many, many different pieces of equipment, this is a real challenge to figure out the overall systematic error, because every piece of equipment has its own systematic error. So that's incredibly challenging, okay, incredibly challenging. But for most cases, we're just going to ignore this. But in the real world, you can't, Okay, the third part, or the third type of error, which is what we're going to be concerned with for the first lab, is random errors, statistical errors. Unpredictable and unknown variations in the total experimental process. So usually these random errors are distributed according to this is called a normal distribution. A normal distribution. A bell-shaped curve, Bell-shaped curve. Okay? So we'll talk more about this in a few minutes. But this is a tough one. All right, so that's errors. Let's talk about some other things that we're going to be talking about. So we'll be using this the whole semester. So oftentimes, we're going to make a measurement of something. And we already, people have already done it. And so we know what the real answer should be. But we're going to measure it, and we'll get close. So oftentimes I'll say, what's a percent error? So here's the formula. The percent error is the difference, right? The experimental value minus the known value. And we want an absolute value, so it's always going to be positive, divided by the known value, multiplied by 100%. So, okay, that's all. So like let's say, so G is 9.8 meters per second squared. So let's say we figured out with our experiment we had G equals 9.9 meters per second squared. That'd be really nice. So the percent error would be the difference, which is 0.1 meters per second squared, divided by the known 9.8 meters per second squared, times 100%. That's how you do it. All right, so we'll do that a lot. Here's something else that we'll do a lot. So let's say we get two values. We don't really know which is we don't have a given, right? Here we have a known or a given, right? Well, let's say we don't have a known, and we just get two values. So what we want to find out is the percent difference of the two values. So, the top is the same, right? Absolute value is the difference between the two values, but the denominator is just the average of the two values, just the average, again, times 100%. So just be careful that you do what you're asked to do, percent error, right? I mean, makes sense, right? Error, if you have a known, then there's an error, correct? But if you don't know that, if you don't have a known, you just have two values, then it's just a percent difference. So, okay, what people usually do with an experiment is you do it over and over and over again. Because, if you just do it once, nobody's going to believe you, right? You're going to do it many, many times. So what we're interested in is repeated measurements. And here are two words which are used improperly in everyday English. So we're going to give you the proper definition, okay? So accuracy versus precision. So accuracy, what it means is how close each data point is to the correct value. On the other hand, precision, how close each data point is to each other. Completely different, right? So let's go over that. So let's say we're throwing darts at a target. So here's the target. So what do you say? Is the accuracy good? Is the precision good? What? Well, you're trying to get it in the middle, right, in the bullseye. And so your accuracy is pretty poor. And then they're not really close to each other, so your precision is pretty poor too, right? So, pretty bad. Okay, how about this one? The accuracy, again, trying to get in the bullseye, so that's pretty poor, but the precision is great, right? They're all close to each other. So how could you explain something like this? Like let's say it wasn't darts, let's say you're shooting a gun with a scope or something like that. How would you explain something like that? Well, maybe there's a systematic error. Maybe the scope is not correctly set up on the gun or something like that. Or maybe you have a twitch. I mean, I don't know, but this looks like a systematic error, Okay, so poor accuracy, great precision. Now what do we want? We want this, right? We want great accuracy, close to the bullseye. We want great precision, close to each other. Okay, let's keep going. All right, so when you have a lot of measurements, which is what we're going to do most of the time, you want to usually find the average. And everybody knows this, right? So average, same thing as mean. So you just add them all up and divide by the number of measurements, right? That's all it is, okay? You add them all up, divide by the number of measurements. I'm sure everybody already knows that. Now, I already talked about this, right? So this is the normal distribution for repeated measurements. So typically, if the only thing you have are statistical errors, this is the number of measurements. Usually, this is the average, right? So usually your data is going to follow this nice bell curve. So we're ignoring personal errors. We're ignoring systematic errors. Okay. So if you do if you do a really large number of measurements, you usually get this nice bell curve. But you have to do a lot of measurements, Okay. Now what we care about. Okay, hold on. So let's say you did an experiment. And you did it like 1,000 times. And I'm not going to label anything, sorry. All right, so let's say you did the experiment 1,000 times, and your data looks sort of like this. Well, are you going to have a lot of confidence in that? I wouldn't, On the other hand, let's say you did it like 1,000 times. And again, this is the number of measurements, right? This is the number of measurements. And your data looks like something like this. Well, pretty bad. Then you got to believe it, right? Because, most of your data is right here, whereas here it's all spread out all over the place. So there has to be a way to mathematically say that this is great and this stinks, all right? And there is a way to do that in statistics, and it's called a sample standard deviation. It just basically tells you how tight this curve is or how wide this curve is. I mean, look at it. So here's the average, and this is the difference between every data point, right? So here, like the average would be somewhere here, but look at, there's this huge difference, right? Here, and all that. Whereas here, every point is really close to the average, right? All right, so look at it. So every point minus the average, you square that, you sum it all, you divide by the number of measurements, square root it. So we call that sigma, okay? That's sigma, sample standard deviation. So if this is really small, it's something like this. If this is really, really large, it's something like that. Now, this is, okay. So, the probability that the measurements fall within a certain range of the mean or average, whatever. Okay, you're going to use this, you're going to refer to this in your lab today. So pay attention. Okay, so this is from the theory of statistics. So again, this is the number of measurements, and this is what you're measuring. All right? And we're assuming we've done a lot of measurements. Okay, so here you go. So one standard deviation away from the mean, so one sigma away from the mean, here's the mean, in either direction. On the horizontal axis, the red area, this is one sigma this way, this is one sigma. So this is like the average, right? So you say like x average plus or minus 1 sigma. So 1 sigma away from the mean in either direction accounts for 68.3% of the measurements. So what we're saying is we have no personal errors, we have no systematic errors. All we have are random errors. If you have a large number of measurements, according to the theory of statistics, 68.3% of the measurements will fall in the average plus or minus 1 sigma. All right? 2 sigma away from the mean, so now I have the red and the green, account for 95.5% of the measurements, okay? So again, no systematic, no personal, a large number of measurements, only random errors. So 95.5% of the measurements will fall in average plus 2 sigma minus 2 sigma, this region. And 3 sigma, the red, green, and blue, account for 99.7% of the measurements. Okay? So, if you had a measurement way out here, what's the likelihood that it's just caused by random errors? Not very likely, right? Because come on, 99.7% are within this. If you're way out here, it's probably a personal error or a systematic error. Okay, another thing that we often use in labs is called the standard error or the precision of the mean. So they use alpha. So there's sigma divided by the square root of n. Uppercase n is the number of measurements. Okay, so this gets smaller and smaller as you have the larger and larger number of experiments, right? So we'll use that in lab. So just you should hold on to this handout because you'll be using it throughout the semester. All right. Now, let's say we're going to, all right, so today's lab is just practice in statistics and Excel. So for today's lab, you're going to use a magazine or a book or I don't care, something like that. And I'll get into details later, but you're going to measure the width 10 times, so you can get an average width. Then you're going to measure the height, or I think I call it length, whatever. Length 10 times, figure out an average. And then you're going to multiply the averages to get the area and da-da-da-da-da. Okay, now look. This has an error associated with it, right? I mean, you have 10 measurements, so you're going to have an error associated with it. You're going to have a sigma width and an alpha width that you have to calculate. Same as here. You can have a sigma length and an alpha length. Gosh. All right? Now the question is, how do you handle these sigmas and alphas when you're multiplying, length times width to get the area? Okay, so here you go. Suppose the area is the average length times the average width, which is true for a rectangle. So the standard deviation of the area is this crazy formula. So don't memorize this, just look it up, So the average length squared times sigma width squared plus the average width squared times sigma length squared. You add it and you square root it. And here's the corresponding equation for the alpha. Okay? So you'll use this. All right. Hold on a second. Okay, let's quit.